So the next property would be, which we have to discuss, is time shifting property, where we have to see that what happens if I do a time shift on time axis, obviously, then what happens with this with the corresponding spectrums on frequency axis. That is, suppose if I have been given with f of t having, say, Fourier transform f of omega, I shall also draw the arbitrary signal over here, and the arbitrary corresponding transform. Let us say this is the transform. Say this is f of omega. Now, this f of omega will obviously be having some magnitude with an angle of f of omega, or I can write it as this phi for f of omega. I have also told you earlier also that this complex exponential is very important signal. The signal is only contributing the phase which is written over here besides j. Its magnitude is always unity. I told you in previous lectures. Now what happens if I do time shifting over here? That is f of t minus t naught. The property says the corresponding spectrum would be having phase differences. It would get a phase lead or a phase lag in this way. F of omega, it would get multiplied with e to the power j omega minus t naught. Same sign. This is what you need to remember. Same sign. Minus t naught. That is, if I look into the picture, what the changes I will be expecting from f of omega and f of omega to the power minus j omega naught. If I see this, the magnitude part of the signal, that is mod f of omega and mod minus j omega t naught. If you see this, I have just told you that the magnitude of this signal is always 1, irrespective of this theta, where this magnitude is mod f of omega. So this will multiply by 1. So there is no change in the magnitude part. It was earlier, it was f of omega mod. You can see it over here. It was f of omega mod, and this is also f of omega mod. So there is no change in magnitude spectrum. But what happens to the phase? Earlier it was e to the power j phi f of omega. Now the phase part would be, this is the magnitude part, that would be the phase part, phase spectrum. The phase part would be, if you see the phases, when the two signals are multiplied, their phases must be added. That is, phase for this signal is e to the power j phi f of omega, and phase for this signal is minus omega t naught. So this would be added with this phase, minus omega t naught. That would be the corresponding phase for this signal, which is different from phi. This much amount of, that is, you can see here, omega t naught amount of additional phase lags would be given onto the phase spectrum. That is the major difference which has happened while doing time shifting on the time axis. That is the effect of time shifting on phase spectrum. But the amplitude spectrum remains unaltered. I think this is clear to you. Similarly, if I do f of t plus t naught, in the same way, I will be expecting f of omega e to the power plus j omega t naught, and magnitude is same, but there is a change in phase obviously. The phase was earlier phi, f of omega for this, and this phase would get added plus omega t naught. So that is the phase now. Earlier the phase was this only. So that is the effect of time advance, which is changing the phase spectrum of the signal by keeping the magnitude spectrum intact, same. I hope this property is clear to you. To illustrate this property more, let us take a few examples. The first example I would be taking is in the form of a question which has also been asked in GATE paper. Properties are very important for competitive examinations in the Fourier Transform chapter. Let us take this example. We have to calculate the Fourier transform for this signal. Suppose that is f of t signal over here. Now, if I look at the signal, this signal is nothing but the combination of two rectangular pulses. As I see them, the question is first you need to find the Fourier transform of this signal. Now, if you look at the function f of t, you can see that this signal is a combination of two rectangular pulses in this way. This is nothing but this f1t. It is added with from 2 to 3. It is added with this signal, say f2t. It's obvious in between 2 to 3, 2 plus 3 will become 5. Now, for these two signals, if you go for Fourier transforms, you need to understand a very basic Fourier transform of a signal called as gate pulse. Now, what is gate pulse? I want to digress from this question to make an important note. You can take it as a note. Gate pulse. Gate pulse is nothing but an even rectangular pulse is a gate pulse. It is also represented with gt of t, where t is the width of rectangular pulse. It is the width of rectangular pulse. The Fourier transform for this signal is t sampling t by 2 omega, where sampling signal is nothing but this signal. You have also seen these signals in communication many times. And in antenna, when you study antenna, you will find this signal very important. It is sine over argument signal. This is sampling signal, pi, 2 pi, 3 pi, and so on, like that. There is also a very important relationship between a sampling signal is sine over its argument. Its argument is t over here. You can see that this is sine signal over the argument t. It is also called sine over argument signal or sampling of t, or you can also see somewhere written as sinc function. Sinc of t is nothing but sampling of pi t. Means if you are doing a scaling factor pi, if you are doing a scaling with scaling factor pi in this sampling signal, you will be having sinc function, which is nothing but something like this. It's very simple, like that. This is sinc function. You can see that these signals are also even signal. They are energy signal, like that. The properties are very important for this signal. And some in mathematics, you can also find a question that what is limit t tends to infinity for sampling t? You can see that this is 0. What is limit t tends to 1 or 0 of sine t? You can see it is 1. You can find this very important for mathematics also. Now, for gate pulse, I would be having a sampling signal as the Fourier transform. That is t sampling t by 2 omega, where t is the width of the rectangular pulse. For example, if I'm talking about GTT, it is the gate pulse like this. Minus t by 2 to t by 2, so that the total width becomes t, and this is 1. So this is gt of t. Now, for this rectangular pulse, you can see that this signal, I don't know the Fourier transform for this signal, but I know the Fourier transform of gate pulse. So what shall I do so that this signal would become a gate pulse? Definitely, I need to do time shifting. So to time shift and to make it a gate pulse, its width is, please check the width of the signal, that is 6. And if you want to make it a gate pulse, it means it is from minus 3 to 3 because it has to be an even signal. So distributed eventually about y-axis or ordinate. So this is minus 3 to 3 with magnitude of 2. This is nothing but the shifted version of this signal. And if I want to make it a gate pulse, similarly, that is 2 to 3. If I say it, it's from 2 to 3 means 1. It's very evident that it would be from minus half to plus half with the same magnitude 3, because time shifting does not alter the magnitude of the signal. I told you it many times. And I can easily find the Fourier transform for these two gate pulses, which is nothing but, if I wish to find the Fourier transform for this signal, it is nothing but, this is minus t by 2 to t by 2. So what is t? T is obviously 6. So this is 6 sampling 3 omega. This would be the answer if it is 1 over here, but it is 2. So it gets magnitude scaled also by the scaling property which we have just discussed. That is not the scaling, it is homogeneity principle from the linearity property, I want to say. So this is 6 into 2 becomes 12. So that is 12 sampling 3 omega. Likewise, if I see that the Fourier transform would be, this is t by 2 equal to 1 by 2, so t equal to 1. So this is 1 sampling t by 2 means half of omega. And because it is 3 over here, so it get magnitude scaled by 3. It becomes 3 sampling 1 by 2 omega. Now these are the Fourier transform for these two signals, but I want the Fourier transforms for these two signals, that is f1 and f2. So what I have to do, what shall I do so that this signal would now become this signal? I have to time shift this signal again. If I do time delay, if I do time delay by 3 units, you can see that the signal will be transformed. So by using the property, if I'm doing time delay by 3 units, that is t to t minus 3, definitely the Fourier transform would be 12 sampling 3 omega e to the power same sign minus j omega into 3, that is minus j 3 omega. And if I wish that for this signal, I also want this minus half to plus half. I want this particular thing to be at 3 and this thing to be at 2. What I have to do? I have to time delay this signal also by how much units? If I'm doing, that is 2 minus minus of half, that is 1.5, 3.5. So if I do that, suppose if I'll be taking minus half, that is minus zero point 0.5, and if I'll be adding this with the say 2.5, I will be getting this as 2. So all I need to do is nothing but this minus half when get added with the 2.5, you will be having 2 over here. It means you have to do the time delay by 2.5. 2.5, say 5 by 2. You can write it like that. We can also write in numerals. Doesn't matter. It is 3 sampling. If I illustrate it, time will be shifted by t minus 5 by 2. The corresponding Fourier transform would be 3 sampling half of omega e to the power same sign minus j 5 by 2 omega. like that. Now, that is the Fourier transform for this signal, and this is the Fourier transform for this signal. Now, if I will be adding them, I would be having this signal, and hence the Fourier transform would be nothing but 12 sampling 3 omega e to the power minus j 3 omega plus 3 sampling half of omega e to the power minus j 5 by 2 omega. That is the answer. I think with this example, the property is clear to you. Let us take the next example to illustrate these properties. If I'll be given with this signal f of t, and also it is given that f of t is having the Fourier transform f of omega, and I will be asked to find the Fourier transform of this signal. Suppose this is g of t. I have to I have to calculate the Fourier transform for g of t, that is g of omega, but in terms of this f of omega. This is what the question is. To do these kinds of questions, properties are very important because all you need to do is to find the relationship between this signal and this signal. And then after finding the relationship on time domain, we can use the properties to get the corresponding frequency domain representations. That is, first I need to understand that what I shall do to this signal so that it would become this signal. So it's a very important application of your basics. It's a test of your basics knowledge. Fourier transform is just the basic applications. Now, if you look at the signal very carefully, you can easily find that if I do shifting of this signal, because the width is all same, this is 1 and this is also 1. So it shows that from the basic three transformations, I don't need to do time scaling because width is almost same. I don't want to alter the width, so time scaling would not be done. And this way we have to think. I need to do time shifting, although because this is at minus 1 and I want to bring it over here from minus at minus half. Let's see what happens next. Now, this signal would be time shifted. So what shall I do to make it minus half to minus 1 to minus half? Definitely, I have to do the delay. That is delay by half unit. So if I'll be delaying it by half unit means this will be added with plus half, so it would be minus half over here. And this plus half would be plus half. 0 plus half is at the plus half. So to do this, let me also draw the graph. That would be the signal after transformation. But still I have not obtained this signal. What shall I do? I can do the time reversal in this way. That is the time reversed version. And then definitely if I add them, I will be having this signal. By adding these two, I will be having that particular signal. So correspondingly, if by utilizing the property, I shall write the transforms. If f of t is having the Fourier transform of omega, then f of t minus half would be f of omega e to the power minus j half of omega. Similarly, if you're doing time reversal of this signal, then what happens? For that, you can also write time reversal property. F of t is having the Fourier transform f of omega. Then f of minus t would be having the spectrum also reversed. That is, f of minus t is having the spectrum f of minus omega. It also got frequency reversed, like time reversal. So you have to replace omega with minus omega everywhere you can find in the expression. That is f of minus omega e to the power plus j half of omega, like that. And if I wish to add them on time axis by using linearity property, their frequency spectrums would also get added. So the Fourier transform for this signal would be, if I write this over here now, f of omega minus j half omega plus f of minus omega e to the power plus j half omega. That would be the answer. I think that question is clear to you. Let us move on to the next property. Now, the next property would be time scaling property. That I want to understand that what happens on the spectrums if I do time scaling on time axis. That is, suppose suppose I have been given with f of t having spectrum f of omega. I shall be drawing it. Say this is the signal. Say minus t to plus t. And here you will be having f of omega. Say minus omega 2 plus omega. Then what happens if I do time scaling on that? If I perform f of at, the property says the corresponding Fourier spectrum would also get scaled, but in reverse manner. That is, if this particular time domain signal is get expanded, then the corresponding frequency signal would get contracted. It is compressed. If this is compressed, then the spectrum would be expanded in the same ratio. That is, if I write this mathematically, this is f of omega by a with 1 by a. That is the magnitude which changes. It's only the magnitude scaling. Because of this scaling, the magnitude is not changed. Because time scaling does not alter the magnitude in time domain. And if you're doing scaling on the frequency domain, magnitude would not alter because of frequency scaling. It is this property that brings this 1 by a over here. So the magnitude is seems to be getting changed, right? Now, I want to illustrate it with the example. Suppose I'll be taking the same signal f of t and f of omega I have drawn. And if I do, say, f of 2t, obviously this will be divided by 2, so it will get compressed in this manner, you can say, minus t by 2, t by 2, and scaling does not alter the magnitude, so it remains 1. The corresponding spectrum would be 1 by 2 f of omega by 2. F of omega is this. If I do scaling by 1 by 2, it would become minus omega by 1 by 2, which is minus 2 omega. Likewise, this is 2 omega. So the corresponding spectrum would be like this. You can see it is expanded when it is compressed. And because of this, the magnitude remains 1. This is what I was illustrating. But because of this property, it is multiplied by 1 by 2. So the magnitude is get multiplied by 1 by 2. It becomes half then. Similarly, if I do f of half t, then I shall be obtaining minus t by 1 by 2, which is minus 2t. Somewhere here, this is 2t, this is minus 2t, and this would be 1 over here, because there is no change in the magnitude while doing scaling. The corresponding spectrum would be 2 f of 2 omega, because the scaling factor a is 1 by 2. So this is 1 by a becomes 2, and that is f of 2 omega. If I do this over here, I will be having f of 2 omega as minus omega by 2 and plus omega by 2. This is this. Magnitude is not altered because of this particular change scaling, but it changes because of this too. So it becomes 2 over here. So you can see that if the time domain signal is compressed, the corresponding frequency representation is get expanded. If the time domain signal is expanded, the corresponding frequency spectrum is compressed. You can see that. One more point. If you see as the concept of gain bandwidth product, this concept says this gain into bandwidth product is constant. But there is no such concept on time axis like gain and pulse width product, gain and time duration product. No, there is no such concept. It is very evident from this property. Like if you do this, gain is 1, bandwidth is omega. If I take the positive frequencies which is having the information, so the bandwidth would be 0 to omega, which is omega. So gain into bandwidth is 1 into omega. Similarly, in this example, bandwidth is 2 omega when multiplied by gain, which is half. This is omega. Similarly, in this example, gain is 2. That is the gain, 2. Bandwidth is omega by 2. This is omega. You can see that the spectrum is having same gain into bandwidth product. But not here. You can see that. If this is gain, 1 into pulse duration t, so this is t, And if you take the total pulse, because time negative time is possible, it can be realized. So it would be 2t. Here it is minus t by 2 to t by 2, which is t into 1, which is t. Minus 2t2 plus 2t is 4t into 1 is 4t. They are not same at all. So this concept does not hold good over here, but the gain into bandwidth product goods very good here. So I hope this property is clear to you. Let us take some examples to illustrate it further. Now, if you will be given with the signal, say, this signal, and it is having the Fourier transform of f of omega. Now, if it is asked to take the Fourier transform of, say, this signal, say g of t, in terms of f of omega, the question is very simple because all you need to do is you can see the width, it is 4, it is 2. So what shall I do so that the width will become 2? Obviously, I need to do time scaling. That is, this signal has to be scaled by 2 over here like that. 2t, then you will be getting 4 by 2. That is 2 here, 0 by 2, and that is 0 here. Now, if the time axis would be scaled by scaling factor 2, the corresponding frequency axis would be getting something like this. 1 by 2 f of omega by 2. This is what happens with the frequency, corresponding frequency signal. That is, if I do it 2t, then one thing which is different is this magnitude. This is the difference. I want this to be 1, and here it is 1 by 2. So what all I need to do is to multiply this signal with 2 only. So I will be having, suppose if I do this, like if f of t is having Fourier f of omega, and if I'll be doing f of 2t, I will be having half of omega by 2, since this half of omega by 2 is the spectrum for this signal. And if you are drawing this signal, you will be having nothing but this. So the corresponding f of this g of t is nothing but f of 2t, and the corresponding spectra would be this. I hope this example is clear to you. Let us take this example one step further. In terms of f of omega, we need to find it. Now, first you need to change the width of the signal. That is, t changes to 2t. The signal becomes something like this. Now I want this signal to be, sorry, say 224. Now I want this signal to be from 2 to 4 and also in the magnitude reverse direction. So magnitude reverse is not a matter of concern because it's just a magnitude scalar which I can do at the end of my question. What I should be concentrating is what I have to do to make this signal shifted at 2 to 4. And it's very obvious that you need to do delay by 2. You will be having your signal over there, something like this, 2 to 4. And then I will be having the magnitude reversed. Correspondingly, the spectrums would be, if f of t is having f of omega, then f of 2t will be having 1 by 2 f of omega by 2. Now, if this signal is having that spectrum, if I do time shifting in this signal by 2, I should be having nothing but half of e to the power minus j2 omega. Now, this is the spectrum for this signal, but my signal is also magnitude reversed. So, all I need to do is to multiply this signal with minus 2. So, the corresponding spectrum, if I write over here, it should be minus 2 into half f of omega by 2 e to the power minus 2j omega. So, that would be the answer. This is minus f of omega by 2 e to the power minus 2j omega. That should be the answer.